In this module, we will be discussing some of the reactions of amines. The reactivity of amines is mainly due to the presence of nitrogen with a lone pair of electrons. The presence of this lone pair of electrons on nitrogen makes it to behave as a base as well as a nucleophile. So all the reactions of amines can be categorized into the reactions where amines behave as bases and the reactions where the amines are behaving as nucleophiles. The basic nature of amines is once again due to the presence of lone pair of electrons on nitrogen, and these amines are generally stronger bases than alcohols, ethers, and they are readily getting protonated even with weak acids. Say for example, triethylamine on treatment with acetic acid gets protonated. So this is the conjugate acid of this triethylamine. The pKa value of this conjugate acid is much higher. The higher value of pKa shows that this is a weak acid. When the conjugate acid is weak, the corresponding base is strong. So the amines are stronger bases to get protonated even with weak acids. And here are some examples where amines are getting protonated with acids. Ethylamine reacts with hydrochloric acid to form a salt here, and this is the conjugate acid of this ethylamine where we find the pKa is higher than 10. That shows it's a very weak acid. Triethylamine similarly reacts with a weak acid, acetic acid, getting protonated to form the conjugate acid, and this conjugate acid also is very weak. So from all this we can understand that the conjugate acids that we are getting from amines are weak acids. That's why the amines are stronger bases. Amines on treatment with the acids form their corresponding salts which are soluble in water, and this is used for the separation of amines from all other organic compounds. An amine can be separated from other organic compounds by converting it into a water soluble ammonium salt by an acid base reaction. Say for example, aniline can be extracted with dilute hydrochloric acid. When an amine is protonated by aqueous acid, its solubility properties change. Say for example here cyclohexylamine, this molecule is insoluble in water whereas soluble in dichloromethane. Whereas once it is protonated, it becomes water soluble and insoluble in the organic solvent dichloromethane. The basic nature of amines are affected by various factors like inductive effect, resonance effect, aromaticity, and hybridization. First of all, inductive effect. A primary amine RNH2 is a stronger base than ammonia. It is because the alkyl group present here is a plus I group which donates electrons to nitrogen and increases the electron availability on nitrogen, making it more basic. When you compare the basic strength of secondary amine with the primary amine, the secondary amine is being a stronger base. It's because of the electron donation by alkyl groups by inductive effect. Coming to resonance effects, whenever an amino group is connected to a minus R group, it becomes a less basic molecule. Aniline and arylamine, where phenyl group is connected to an amino group, is less basic than ammonia or alkyl primary amine. This is because the phenyl ring present in aniline is a minus R group. It is withdrawing electrons from nitrogen through resonance so that the electron availability for on nitrogen to behave as a base decreases. As a result, it becomes less basic than ammonia or alkyl primary amine. Similarly, when the amino group is connected to a carbonyl group, in case of an amide, carbonyl behaves as a minus R group and it withdraws the electron from nitrogen. Lone pair of electrons from nitrogen is withdrawn by carbonyl group. So the electron availability on nitrogen decreases. So the basic nature of this molecule also is less than the corresponding alkyl amine or ammonia. The next point is aromaticity. Let us understand this concept by taking two examples, pyrrole and pyridine. In pyrrole, the lone pair of electrons on nitrogen are involving in delocalization to make this molecule aromatic. Whereas in pyridine, the lone pair is not involving in delocalization, it is freely available on nitrogen. So this is more basic than pyrrole because of the lone pair availability on nitrogen. So this delocalization of lone pair in pyrrole takes place to make this molecule more stable aromatic. The next point is hybridization. This also we can explain by considering two examples, pyridine and piperidine. In pyridine, this nitrogen is sp2 hybridized, whereas in piperidine it is sp3 hybridized, where in piperidine nitrogen is sp3 hybridized and the S character is only 25%, whereas in piperidine nitrogen is sp2 hybridized and the percentage S character is higher than the percentage S character of piperidine. So as S character of the hybridization of nitrogen decreases, the basic strength increases. So here it is sp2 nitrogen, this is sp3 nitrogen, this has less S character and is more basic. Amines can react as bases and they can react as nucleophiles. When an amine is treated with an aldehyde or ketone, it reacts as a nucleophile. The carbonyl carbon, as we know, is an electrophilic center. As a result, it can be easily attacked by the nucleophilic nitrogen of amine. So this nitrogen of amine reacts as nucleophile with the electrophilic carbon of the carbonyl compound. So nitrogen, when attacks the carbonyl carbon, this pi bond is shifted to oxygen. Then by a proton transfer, it becomes a carbonyl amine or aminol. The mechanism also we can see here. The amine attacks the electrophilic carbon, pi bond is shifted to oxygen. Then by proton transfer, it becomes carbonyl amine or aminol. Since we are using a mild acidic medium, the acid protonates the OH. So now after protonation, it becomes a better leaving group and it is readily pushed out with a lone pair of electrons on nitrogen here, resulting in the protonated imine that loses a proton to water and forms an imine. So a primary amine can react with an aldehyde or ketone as a nucleophile and can result in the formation of an imine. Similarly, a secondary amine also can react with a carbonyl compound, an aldehyde or ketone, where the nucleophilic nitrogen attacks carbonyl and this becomes OH, and now the OH gets protonated with the acid that is pushed out by the lone pair of electrons on nitrogen, and then The bond is taken back and this hydrogen is removed. So the deprotonation now happens from the beta carbon. So as a result, you get a double bond between alpha and beta carbon atoms, and that is an enamine. So the end product of the reaction between an aldehyde ketone with a secondary amine is an enamine and not an amine. Ammonia, primary amine or a secondary amine, can react with a carbonyl compound with a good leaving group and can cause a nucleophilic substitution. So here ammonia behaves as nucleophile and it attacks the electrophilic carbon and is pushing out the chloride. So there is a nucleophilic substitution here. An acid chloride reacts with ammonia to give a primary amide. Similarly, a primary amine can react with an acid chloride to form an amide, which is a secondary amide. A secondary amine can also react with an acid chloride that results with a tertiary amide. And we shall take one example of the reaction between acid chloride and amine, which is a very useful reaction. So here we have an acid chloride that reacts with the diethylamine that results in the formation of a product that is NN-diethyl metatoluamide. This molecule is an active ingredient in the most widely used insect repellents and it is very effective against mosquitoes. So in all these reactions we have seen amines are behaving as nucleophiles and substituting the nucleophile that is already present in the molecule. And there is another similar reaction where the ammonia or amine react with an acid anhydride where we find a very good leaving group carboxylate. Here ammonia reacts with acid anhydride forming an amide. And this is another example for nucleophilic substitution reactions of amines. And we can consolidate all the reactions we have discussed so far. That is the reactions of acid chlorides and acid anhydrides. Here Z can be chloride for acid chlorides or it can be a carboxyl group for acid anhydrides. And both result in the formation of amides. And the conversion of an amine into amide is very often useful for us in synthesizing the derivatives of aromatic amines. So for example, aniline does not undergo Friedel-Crafts alkylation reactions in the presence of a Lewis acid because when aniline is added to a Lewis acid like aluminum chloride, the nitrogen with its lone pair makes a complex with the aluminum. The vacant orbital of aluminum, the lone pair of electrons on nitrogen interact to make a bond here, and the nitrogen, as a result, nitrogen gets a positive charge. Once nitrogen gets a positive charge, it becomes a highly deactivating group, so that this aromatic ring which is attached to a highly deactivating group cannot undergo any alkylation reactions. So how can we carry out the Friedel-Crafts alkylations in aromatic amines? First of all, we can convert the aromatic amine into an amide by treating with the acid chloride. So here an aromatic amine aniline is treated with acetyl chloride to get acetanilide. Then you can carry out the Friedel-Crafts reaction. Now the lone pair availability is less on nitrogen. As a result, it cannot readily form complex with the Lewis acid. Instead, the normal Friedel-Crafts reaction takes place here. And finally, this amide can be hydrolyzed into amine. And this is an useful way for us to introduce an alkyl group into an aromatic amine. Another very important reaction of amines is Hoffman elimination reactions. In case of a primary amine, we can treat it with the excess of methyl iodide or some other primary alkyl halides, and we will end up with a quaternary ammonium salt. And this quaternary ammonium salt on reaction with a base will undergo an elimination reaction to give you an alkene. And this reaction follows E2 elimination mechanism. For E2 elimination reaction to operate, the two groups which are eliminated have to be anti-periplanar. And this E2 elimination reaction, unlike the other E2 elimination reactions, leads to the formation of a less substituted olefin. That we can understand with an example here. This is an amine. On treatment with a excess of methyl iodide, we get quaternary ammonium salt. And this on treatment with a strong base like hydroxide can undergo elimination. This hydroxide can abstract hydrogen from this beta carbon either or from this beta carbon. But normally the hydroxide prefers to remove the hydrogen from this one, the less substituted beta carbon, leading to the formation of a less substituted olefin. So Hoffman elimination of a quaternary ammonium salt always leads to the formation of a less substituted alkene, the Hoffman product. And here we have another reaction where the amines are behaving as nucleophiles. Ammonia can react with a primary alkyl halide to form a primary amine. The primary amine can once again react with another alkyl halide to give a secondary amine that can further react to form tertiary, that can undergo further reaction to form quaternary ammonium salts. And these are some of the methods we use for the preparation of primary amine, secondary amine, tertiary amine, and quaternary ammonium salts. Another very important reactions of amines is the reaction of amine with nitrous acid. Nitrous acid is a weak, unstable acid, and it is prepared in situation where it is required by treating sodium nitrite with hydrochloric acid. So hydrochloric acid and sodium nitrite react to form nitrous acid. This nitrous acid can be further protonated with hydrochloric acid, and with the removal of a water molecule from this, we end up with nitrosonium ion. This nitrosonium ion is the electrophile that can react with a primary amine, alkyl amine, to form an alkyl diazonium salt. With an aryl amine, it can react to form aryl diazonium salts. So whenever we want to generate an alkyl or aryl diazonium salts, we treat the amines with sodium nitrite and HCl. The mechanism of this reaction is given here. The nitrosonium ion, which is generated from sodium nitrite and hydrochloric acid, the electrophile, is attacked by the nucleophilic amino group. The resulting species can undergo deprotonation to form N-nitrosoamine. This N-nitrosoamine can once again be protonated. With the removal of another proton, once again we will end up with this product, and that on treatment with the reaction with the hydrochloric acid, as shown here, we end up with the diazonium salts. And if you just go through this slide, the mechanism is given in detail very clearly. It's self-explanatory and you just can go through. And one important point about the diazonium salts is diazonium salts are very much less stable and they decompose even below the room temperature to form carbocations with the loss of nitrogen, since the nitrogen is a very good leaving group. So after the removal of nitrogen, we will end up with a carbocation. This carbocation can undergo elimination reactions, substitution reactions, or it can undergo other reactions after undergoing rearrangements. If aniline is treated with sodium nitrate and HCl, we end up with this benzene diazonium salt, and this is an useful intermediate in the preparation of many aromatic molecules. So benzene diazonium chloride, on treatment with cuprous bromide, we end up with bromobenzene. Diazonium salt with the cuprous chloride, we get chlorobenzene. With cuprous iodide, we end up with iodobenzene, and with cuprous cyanide, we end up with cyanobenzene. And this is the reaction we have learned already as Sandmeyer reaction. The diazonium salts can undergo coupling reactions with the activated aromatic molecules. So here you have aryl diazonium salt that reacts with the activated aromatic molecule to form a coupled product. And as the best example, we can consider the reaction of aryl diazonium salt with phenol. So here phenol reacts with the diazonium ion to form an azo dye, a coupled product. And these are some of the reactions of amines, and there are a lot more to learn about the reactions of amines, but in this module we end up here.